In this video, we will look at some of the findings from the literature on price and income elasticities in order to better understand how changes in tariffs and income affect water use by households with piped connections. Economists try to explain the quantity of water used by a household with a piped connection as a function of the price of water, the income of the household, the price of closely related goods and services, and other variables. As the price of water goes up, it is expected that the quantity used will go down, but by how much? And as household income goes up, the amount of water a household uses is expected to go up, but again, by how much? Water resource planners need to estimate how households will react to changes in prices and incomes in order to estimate the amount of water that will need to be supplied in the future. Other variables besides price and income are also important determinants of a household's water use. The most important are the number of household members and whether the household has the opportunity or option to use water for gardening and other outdoor uses. Also, as temperature increases, households use more water, both for bathing and washing, and for outdoor uses. Economists use the concept of elasticities to describe how much changes in tariffs and income affect the amount of water a household uses. This price elasticity of demand for piped water is the percentage decrease in the quantity of water used for a 1% increase in the price of water. The income elasticity of piped water is the percentage increase in the quantity of water used for a 1% increase in household income. Note that if water tariffs and household income are both increasing, these two effects are pushing in different directions, and depending on the magnitude of the two elasticities, they may to some extent cancel each other out. This slide summarizes the range of price elasticities of the demand for water in the United States for different water users. As shown, the residential outdoor use is the most responsive to price increases. This means that as water prices go up, outdoor use decreases significantly. Households in wet climates are most able to reduce their water use because rainfall may preserve their gardens, lawns, and shrubs. Households in dry climates are less able to rely on rainfall, and their demand is more inelastic, at least initially. The response of individual outdoor water users to price increases may not be smooth or continuous. Big changes in outdoor water use can occur if households change landscaping decisions by, for example, abandoning lawn watering or water-intensive shrubs in response to water price increases. Indoor household water use is the most price inelastic. In the United States, estimates of price elasticities of indoor household use are in the range of -0.1 to -0.2. This means that a 1% increase in price causes a 0.1 to 0.2% decrease in indoor household water use. The evidence from the United States suggests that the price elasticity of industrial water use falls somewhere between that of outdoor residential and indoor residential. Industrial price elasticity is in the range of -0.5 to -0.8, but can vary significantly for different industrial sectors and individual industrial facilities. In their review of the literature on water demand in developing countries, Nauges and Whittington summarized the findings on price and income elasticities for household water use in low and middle-income countries. They report price elasticities for households with pipe connections between -0.3 and -0.6. Note that these estimates reflect changes in both indoor and outdoor water use. Indoor water use alone will be more inelastic, for example -0.2. They report income elasticities of +0.1 to 0.3. This means that a 1% increase in income would result in about a 0.2% increase in household water use. These estimates of price and income elasticities have three important implications. First, household water use is price inelastic. As utilities increase water tariffs, water use will decrease somewhat. Second, as tariffs increase, utility revenues will increase. Third, economic growth will put upward pressure on household water demand. The next question we want to ask is how metering affects household water use. Without a meter, it is impossible to set volumetric water prices, so the shift from an unmetered piped water connection to a metered water connection is a discrete change from a zero marginal price of water to a positive marginal price. This slide shows a cross-section of utilities in Brazil with different amounts of metering. Note that the vertical axis is cubic meters per month per customer, not per capita. As the percentage of customers with a meter increases, average household water use falls. Without meters, households can waste very large amounts of water because they have no incentive to fix leaking faucets and toilets and so forth. This effect of metering has been especially dramatic in the countries of the former Soviet Union. In the next series of slides, I will illustrate graphically how changes in water tariffs and household incomes can interact to affect the quantity of water used in a large city in a developing country. Suppose that a water sector reform process is initiated in the city. This sector reform process will improve the quality and reliability of water services provided. Financing will be needed for the investments to augment the water supply and improve water quality. Tariffs will need to be increased to repay these loans. What will happen to the water use of the average household connected to the pipe distribution system? Will it increase, decrease, or stay the same? Before the sector reform effort begins, the tariff is at P1 and the quantity of water used is Q1. Suppose the first step in the reform process is to improve the quality and reliability of water services. These improvements in service cause an outward shift of demand of the demand curve. Because the tariff has not yet changed, the quantity demanded at price P1 increases to Q2. The next step in the sector reform process is to raise tariffs in order to increase revenues, in order to repay the loans used to finance the investments that increase the reliability and quality of water services. Suppose the utility increases prices to P3. In response, the quantity of water demanded decreases to Q3. The new equilibrium is at P3, Q3. But this is not the end of the story. As economic growth proceeds and household income increases, the demand curve for water shifts further outward. In this figure, the final equilibrium is reached at P3, Q4. Q4 could be greater than, less than, or equal to Q1. The point of this illustration is the quantity of water used in a city over time is the result of the interaction of several countervailing factors. 1. The magnitude of the improvements in service and how much these increase demand for water. 2. The magnitude of the tariff increases needed to increase revenues, which will depend on the cost of financing. And 3. The size of the price and income elasticities in the particular city at a specific period in history. To wrap up, the literature suggests that household demand for water from pipe connections is inelastic in both industrialized and developing countries. Indoor water use is much more inelastic than outdoor water use. And as household income increases, water use increases modestly. In the next video, we're going to look at households with water sources outside the home. Thanks for watching this video.